So before I start, I would like to thank the organizers for inviting me and to give this talk. And this talk is about a recent work with Rahul Jain and Penguyo, who both of them are here. So I prepared an outline, but I will skip most of the introduction because this has been covered in the previous two talks. So I don't want to bore you so much about it with that. And instead, I'll talk about what is our result, and then what is the broad idea of our proof, and depending on how much time we have left, some of the details of the proof. So maybe I still show this, although this is like all the same, the n+1 version of the same picture as before, but maybe the notation will be, I think it's a bit different than the previous talk. So usually, the shared state by phi, and then the questions to Alice and Bob by x and y, which is drawn from some distribution mu. And then after Alice and Bob receive the questions, they measure the state phi and then reply back A and B. Okay, so all these comes from some finite sets. And then the verifier evaluates the predicate V, and then if it's 1, then then they said that the players win, and the value of the game is the supremum of the achievable winning probability, which is denoted by omega star G. So this is all the same as before, and also so we denote the k repeated game by G to the k. So it's exactly the same as before. It's k copies of the game G are played in parallel. So in this case, the question is questions and answers are set of are vectors, and the probability distribution is k in the so each xi yi is distributed according to mu independently. Okay, and then. So the players win if they win all the instances. Okay, so this is all the same. So I won't talk about the per repetition theorem because this has been covered before. So I we just skip straight away to our theorem. So we have that for any game G, where the input distribution mu is product across the players, then it holds that the value of the game goes down exponentially. And to know that this exponent only depends on k and the log of the size of the questions. So this also has the same form as the per repetition theorem of Raz is for classical games in terms of the exponent. Okay. So maybe I go straight to the proof. During the talk, I will usually say that we condition on success on some coordinates. So, yes?
I know it's the one out. It doesn't imply the previous results.
Which?
Does this result imply innate into last result in the
So I think it's not comparable because they had a restriction on the verifier's predicate, right? That it's a projection game. So here we have all games, but have a restriction on the distribution of the questions. So I think it's incomparable.
So what's the restriction on the distribution then?
So we have product. So basically the questions are independent to the players. So the previous had uniform, right? So yeah, correct.
Because the parameters are slightly different, because here there's a cube.
So yeah, this is
the one there was a square, but with something. But yeah, I mean it's basically. So it's a bit of power.
Yeah, so we have cubed, but here we don't have x and y, the size of answers. We only have sorry, we don't have the size of questions. We only have the size of answers.
So these examples where exponential scaling doesn't happen, at least for a few rounds, Do we have examples like that?
Actually, I don't know. Do we?
Yeah, it's a two-round with product distribution.
In product?
But not for a moment and discuss.
Okay. So the broad idea goes along the same line as the proof of Raza and Holenstein for classical games. So we say that in GK, G to the K, we condition on success on some set of coordinates, which I call C. Okay. So basically, this means that conditioning on success means that success in these coordinates is basically a projector. So we say that whatever the state of this whole system, we just project to success on these coordinates and then rescale. So you can, whenever I say condition on success, this is sort of what it means. So there are two cases. If the success probability is already small enough, like if it's exponentially small, then we are happy and then we are done, because that's the theorem. So, and otherwise, we show that there is some coordinate j outside of this set C, such that success in the jth coordinate conditioned on being successful in C is bounded away from 1. So if we do it like omega k times, so means that we add j to C and then look for another j and then add to C, set C, and then we keep doing this omega k times, then the success probability will be exponentially small in k. So that's like the broad idea. So how do we bound success probability away from 1? So we have let's have an input to G, like one instance of a game, and what we show is that the player can embed this input into this jth coordinate and then generate the rest of the state in this G to the K. Of course, this is conditional on being successful in C. And then, so maybe I draw something to here. So suppose Alice and Bob gets x prime y prime. Then they want to generate a state in G to the K. So basically, they have to generate the rest of the other inputs for the other coordinates. And then there's also some shared state. So this is so basically, they want to generate a state for which this jth coordinate has x prime and y prime as a question, and this state is also it's been conditioned on success in some coordinates, say here. So once they receive the question for G, then they generate the state of G to the K, then they play the game G to the K, and then they would answer A, which is like A1 to AK. So we only care about AJ. And similarly here we have, let's say, BJ. So this is playing one instance of G. So if they are if they can win this jth coordinate with high probability, that means that they also can win G with high probability. So it means that success in winning the jth coordinate should be bounded away from 1. So this is quite general. I mean, like, this is still a bit broad. So so let me talk about how to generate or how to embed one instance of G into the G to the K. So basically, how to generate this state. So let's suppose without loss of generality that, so when I say the state of the whole system, I include registers for all questions and all answers. Okay, so so in G. So let's say that we have a register x1 to xk, and then we have answer registers a1 to ak. Then there is some shared state, so all this is Alice. Then there is Bob's answers, and Bob's questions. So these are the registers for the whole state. So with a loss of joinity, we can say that when Alice and Bob receive the questions, what they do is they apply some unitary operation on, based on the particular x they get, they apply some unitary operation on this register A and the half of the shared state, and Bob does likewise. And after that, they just measure of these registers in the standard basis and then answer back to the referee. So I mean, nothing happens here. This is just like sort of a different notation. So then we can write the global state of this system as in this form, and also this state is also conditional on success in some C. So let us have so this phi xy is the one that's shared and it also contains the answers. Okay. So
question.
Yes.
So if you're conditioned on success in some coordinates.
Oh, there should be actually rescaling. I mean.
But why should the input distribution, I mean the distribution of x and y, be product anymore?
I mean, actually it isn't. It's. I mean.
You can hide anything you want.
Yeah, you can. I mean, there also should be like a rescaling, like,
okay.
and then something. You can put whatever is here. Maybe I should have just put maybe like some number here or some coefficient. Okay.
And the answer, sorry, the answer, did you write them somewhere?
So the answers are in this also. So okay, so let's suppose that now we have to take a strategy for G. So we want to do this. Let's take a strategy for G, where they share this state phi. So from this state, they want to generate the corresponding state in G to the K. Okay, so this is. I mean, so now we take the purification of the previous state. So, I mean, at this point it's not clear why we take purification, but I mean it was actually in the previous talk. So we eventually want to use Ullmann's theorem. So, but anyway, so let's say that they share this state. So if basically we just copied x into some x register and also same for y. So if you trace out this x register, you just get back the original state. Okay, so this is a purification. So let me propose a strategy for G. So Alice and Bob get questions x prime, y prime. Okay, and then they want to produce this, generate this state. So it means that they want to have, so what they share here, they have superposition in the jth coordinate, but they want x prime in the jth coordinate, the value x prime that they get as a question. So one way to do it is they can just measure this register xj, and also Bob measures yj, and then if they're lucky, they get x prime and y prime, in which case they successfully generated the state, right? Because that state is exactly the state that they want to achieve, that they want to have the question in the jth coordinate. So which means that once they generated this, they can just further measure the answer registers and then reply it back to the referee. So it means that this answer is distributed exactly the same way as was the answer in the game GK when we condition success and conditioning all the input of in xj being x prime and yj being y prime. So which means that this way we embedded a single instance of G into the GK with being conditional success in C in the game GK. So again, if the value of the game is bounded away from 1, then success in the jth coordinate must also be bounded away from 1. But of course, I mean, it doesn't work like that because the probability of when we measure xj in this coordinate, right, then the probability that we actually get the the correct x prime, it can be arbitrarily small. So the question is there a way to generate this post-measurement state approximately without doing measurement? And then the answer is yes, if the distribution is product. So the distribution of x by y prime is product. Okay. So I have one slide of how to do it without measurement, but actually some of these slides has already been, some of the material has already been in the previous talk. So as a notation, let's denote phi x j prime be the state when Alice measures this xj prime and then gets small xj prime. Sorry, when Alice measures register xj and gets outcome small xj prime. Okay, so basically the state phi condition on register xj being small xj prime. And similarly, we define phi yj prime and phi xj yj prime. Okay. So what we show is that in this state, in this state that I showed previously, in the superposition state, we show that the mutual information between this question in the j coordinate and whatever Bob has is almost zero. And similarly, the mutual information between Bob's question and Alice's state is also almost zero. So basically there exists a coordinate for which this is true. So what this means is that if the mutual information between the question of Alice and the state of Bob is like zero, then it means that Bob's part of this state when we measure of the post-measurement state is independent of the actual outcome of the measurement. So basically whatever outcome we get in this coordinate, it won't change the Bob's part of the state much. So which in other words means that getting different outcome is just getting different purification of Bob's state. So we can apply the unitary equivalence of purifications and say that there must exist some unitary on that Alice can apply, which brings this state phi close to the post-measurement state. So instead of measuring xj, then she can just apply a corresponding unitary and get the state which is close to the post-measurement state. So of course this is symmetric, so there is also exist a unitary for Bob, which he can apply to get the state close to phi yj prime. Okay, so of course natural question is what happens if they apply these two unitaries together. And actually this has been shown by a paper of Rahul Jain, Giacomo Krishna, and Pranab Shen, that if the distribution of these xj yj prime is product, then if they apply the two unitaries together, then they actually get this state close to the correct post-measurement state.
Where does the fact that the distribution is product, it comes in because when you write the slitters, you actually mean it on average over x prime and y prime? Or?
So for this to hold, it must be that xj and yj.
Yeah, but I mean the way you wrote the equalities, it seems like they're for fixed x and y. I mean there's no distribution that shows up in any of the statements that you've written in the slide. So that's why I'm asking which.
Oh,
if it's because you're actually measuring.
So this is all true for most of the x, and so it's expectation over xj yj. So for most of the questions, this is true in
so
expectation.
The two conditions hold with on average over the marginal distribution, and then you get the conclusion on average over the product distribution.
No, so actually, if the distribution is not product, right? I mean, one doesn't even get the first line.
Yeah.
I mean, one gets it conditioned on yj and conditioned on x.
So since Bob has also his questions, so if the questions are correlated, I mean, it never be close to zero.
So you need product. I thought you were saying you needed product to go from the second to last bullet to the last bullet.
No.
Well, as well as here.
No. So the thing is that when one does a reduction, right, like to a single game from many games. So then if it's non-product, we don't know how to get that kind of a statement.
You see, okay.
Yeah. So the only statement that we can get is conditioned on yj conditional x.
Then the first bullet, how do you justify that?
So this we can show via like information T argument, like which uses, for example, the chain rule of mutual information.
Okay.
Or, I mean, I don't know if I will have time to.
No problem. Thanks.
So the first bullet, of course, is not true in its current form. If this is not a product distribution over the questions, but I probably can correct it, right? So I mean, what is the obstacle of making this work for non-product?
So in the general case, we have that the mutual information between xj and Bob condition on yj is like is small.
Okay. And that you can probably get here too, right?
No, I mean this is if for whatever distribution the xy come from. I mean this is like general, not for product. So for product we have without this.
Right. Yes. So what prevents this proof for working for the non-product case?
So
Where's the obstacle? I guess this
I mean-
overweight result only works where it's a product.
well, if it's condition on yj, then I mean then there is no unitary which just depends on x or like. I mean if this means that whatever like Bob's whole state is independent of Alice's question, but this if you condition on yj, then I mean the unitary, it's not like there's a unitary which is just depend on this because you condition on this.
So you can think of some other thing that would work. Maybe it's a unit.
No, I don't. We don't know. But so, I mean, of course, this statement can be useful to prove the general case, but how much time do I have?
5 minutes.
Okay, so maybe I just show the statement of the lemma for this replacing the measurement with the unitaries. So, and it's probably the same lemma as appears in the previous talk. So if we have a state of this form, where this phi is shared between, so this phi is shared between Alice and Bob, such that xx tilde and some parts of this psi is with Alice and the rest of the psi is with Bob. And so phi sub x is just a state of phi condition, register x being holding the state small x. So if the mutual information is at most epsilon, then there must exist some unitaries that x and Alice space such that for most of the questions, so expectation over the questions, the trace distance between phi x and the state that we get if we apply ux to phi is at most some constant times square root of epsilon. So this is actually the proof of this is easy, and it just follows from Ullmann's theorem and unitary affirmance of purifications. And the two-sided version is also looks the same. So let's have a distribution mu, and we denote the marginals by mu x and mu y. So we have this shared state again, where the x's are with Alice and the y's are with Bob, and this psi is again shared between them. So if we have the two corresponding mutual information smaller than epsilon, then the unitaries that the previous lemma gives us will give us the following bound. So basically it means that for most of the questions, the trace distance between phi xy and the state that we get if we apply both unitaries into phi is at most square root of epsilon plus some constant times the L1 distance between mu and the product of its marginals. So, and this has been proven by Rahul, Giacomo Krishna, and Pranavchan. So, okay. Maybe I just show this lemma and then end the talk. So basically, the per repetition theorem follows from this lemma directly. So let's have some small constants, delta 1, delta 2, delta 3, for which this following condition holds. And then let's take some k prime, which is a constant fraction of the coordinates. So we take a constant fraction of coordinates. And the lemma says that given any quantum set of g for g to the k, there must exist a set of coordinate k prime, such that for each L between 1 and k prime minus 1, either what happens is that the probability of success in the first L coordinates is already exponentially small. So this t to the L is just the probability of success in I1 to IL. So either the probability of success is already exponentially small in k, so in which this already implies a theorem, or if this doesn't happen, then what we show is that the probability of success in the L plus 1 coordinate, given that we were successful in the first L coordinates, is upper bounded by the value of a game plus some small constant. So if we do it like since k prime is like a constant fraction of k, this will give a exponential decay in k. Okay. So I will skip the proof and maybe just go straight to the end. So this is the theorem that we have proved, and this improved upon the previous result by generalizing it from uniform to product, and by removing the dependence on the size of the questions in the exponent. Although we have 3, and then the previous result had 2. And maybe as an open problem, of course, that a per repetition theorem of this form for general games is still unknown. And with this, I would like to thank you for your attention.
Back to your previous slide. So you say general per repetition theorem where the exponents only depends on k and a size of a times b. If you add size of x and y, do we know it?
No. I mean, they also have some. If for general games, they have a result, but they also have one some other parameter which depends on the minimal probability or the smallest probability of questions, right?
Yeah, I mean, yeah.
So it's not just A, B, X, Y, but there's
here, I guess you could also generalize this to general games, and you would also have the same, because it's just like an adult,
yeah, but general games which give some epsilon value to any pair of questions. If there is some pair of questions that is missing, I think then we don't.
No, because it's the minimal. When there's this weight appears, it's the minimal non-zero.
Yeah, but if the minimal non-zero is 0.
No, the minimal non-zero.
No, minimal is 0.
Minimal non-zero is not 0.
Yes, that's.
It always works.
Okay, so if that's the minimal non-zero, if you can
forget, right? Exactly. So.
Okay.
So it works, but it would be very bad. So if you want to apply it somewhere, it will not work. In general. Depending on what you want.
Other questions? Let's thank Attila again.